a neuroscientist and physical therapist at the University of British Columbia. She is a professor and has held a Canada Research Chair, a Michael Smith Foundation for Health Career Scientist Award, and been a Peter Wall Early Career Scholar. Dr. Boyd directs the Brain Behavior Lab at the University of British Columbia. Her TED Talk, After This, Your Brain Will Not Be the Same, has over 25 million views. Dr. Boyd is an expert in mapping how behaviors, environments, and experiences affect brain health and learning using techniques such as magnetic resonance imaging and non-invasive brain stimulation. To date, this work has largely examined the impact of exercise and learning on neurobiology. In 2020, she was a Wall Scholar, focusing her work on the importance of the arts for brain health. So for those that don't know, what does it mean by the phrase that the brain is plastic, or, what is quote unquote neuroplasticity?
Yeah. So in a nutshell, your brain is changing all the time, and it can change in three ways. And all those ways they're all changing at the same time. Like, I'll describe them separately, but they're happening together. So when we first are learning something new, the fastest and kind of the most short-term way our brain can change is by changing its chemistry. So you have to know a little bit about how the neurons, the brain cells work. So you have your neurons, you have tons of them. We have 100 billion in the brain, so it's not a trivial number. And they're sitting very closely packed to one another, but they don't actually touch. Like, I like to think of them as like touching. They don't. They're very, very close to one another, and there's a very small space between them. So the way that they communicate one neuron to the next is by releasing chemical packages. It's called neurotransmitter. And so you can alter the excitability of the brain. You can kind of turn it up or turn it down by increasing or decreasing the neurotransmitter, the chemistry that's available. So we can very rapidly change the amount of this neurotransmitter that's in certain parts of the brain. And so that's the first and the kind of the short-term way that it can change. If you learn something and you have it in your short-term memory, like you meet someone at a party and they introduce their name and you have that name for a fleeting amount of time, that would be a chemical change probably supporting that. So that's the first way that you're plastic. The second way is actually by changing the structure of your brain. Mm-hmm. So our structure is a little more fixed. It tends to be it's more hardwired. Think about it like freeways on the road. They're going certain places, but if you have a single lane highway versus a 5-lane freeway, the speed can change. So that's one thing that can happen. So we can get thickening and thinning of brain areas that allow things to transmit faster or slower. And then things that we practice a lot, we tend to have, more brain devoted to it. It's almost like, working out at the gym, getting bigger biceps. So if you're a violinist and you're practicing a lot with your fingering hand, that the finger representation in your motor cortex also gets bigger. So you've kind of buffed it up through the practice. So you have your chemical change, you have your structural change, and then lastly, you'll have a functional change. You could turn different parts of your brain up and down with different intensities. So as you learn something and get really good at it, you actually need less brain. So your brain can turn down and be more efficient to do other things. So you change your chemistry, you change your brain structure, and then you change your brain function. Then all those three kind of working together, that's neuroplasticity.
So what is electrophysiological? What are the electrophysiological methods or approaches that are appropriate for assessing neuroplasticity in humans?
Right. So this is a big technical thing. So electrophysiology, what is that? So we now have tools that we can use to both record from the brain and then also map brain changes, and then also speed brain changes. So you kind of have three categories there. So the first one's an old idea. So everyone's probably heard of an EEG, or an electroencephalogram. So you put on the cap, and you have these little recording devices, and you're recording the electrical potentials off the top layer of the brain. And you get these big squiggly lines, and you can kind of infer things about cortical excitability around that. That's been around for a long time. Those techniques are now really, really highly refined. So we just have a new system, and we're installing in my lab actually on Thursday, where you have it's a neural net. So the whole brain is almost covered with electrodes, 256 of them, very dense. And so you can get these beautiful arrays of activity. So that's one piece of this electrophysiology. The part that we've done more of in my group, and we're really excited about using, are ways where we can map excitability changes in the brain. And the way that we can do that is we have a device called transcranial magnetic stimulation. So what it is it's an electrical coil, and it actually induces a current into the brain. It's painless, and it's a current that is electromagnetic, so it passes through your scalp and your skull, and it just kind of feels like a tap. You don't actually feel it. You don't feel a shock. And so we can actually use this approach to assess how excitable brain regions are, because we can see we need more or less a current to pass in to get a response. And so this is a way that we can actually map the physiology of the brain, and we can map changes after brain damage. One of the key questions we have after stroke is the wiring between the motor areas of the brain and the hand still intact? And sometimes a person can't move their hand, but we can put electrical current into the hand motor area and evoke a twitch. And then we know that, for example, if you will, the wiring is still intact. So that's a really positive sign for stroke recovery. But then last, you can drive trains of this stimulation into the brain using this transcranial magnetic stimulation. And you can actually, for a short period of time, excite or inhibit brain regions. So this is the basis of new therapies for depression, which are now FDA approved, very widely accepted, very, very effective, low cost. There's no pharmacology, very few side effects. It's now being used also for obsessive compulsive disorder. And then there are many of us working to expand that out as a therapy for stroke or brain injury. So that's kind of together, you have all these different tools that you can kind of package together. There's one more approach, and that's called transcranial direct stimulation. And this is where you actually wear two stimulators on your brain. You actually pass a current through the brain. So you excite one area and you inhibit the other, where the current comes and goes. And that's another approach to kind of exciting the brain to try to speed recovery. There's a catch with all of these approaches, though, and that is they're not the treatment. So they're an adjunct to the treatment. So if I pass a current through your brain, you won't get any better. You won't learn any more. What I will do, though, is I'll pre-excite your brain. And then if you pair that with something else, trying to learn a new motor skill, for example, or in the instance of depression, cognitive behavioral therapy, then you get this really big response. So we talk about them as priming or preparing the brain to learn. You still have to do the learning bit, though. You don't get to get out of doing the homework, if you will.
Right. No, of course. For those that don't know, I guess the underlying causes and what happens with the brain, what is a stroke, and what are the changes that we can see in a stroke, and then what type of strokes do you quote unquote specialize in or do more research on, or is it just strokes across the board?
Yeah. So we tend to look at stroke across the board. I don't do as much with pediatric stroke. So I'll back up and say what stroke is. So stroke is just a disruption in blood flow to the brain, period. And it doesn't really matter how that happens. There's basically 3 different ways it can happen. The most common way is what we call an ischemic stroke. And that's what we see mostly in older adults. So there's a blockage in a blood vessel. So stroke is basically plumbing at some level. And if you block the pipe and the blood can't get through, brain cells die. We see strokes in older people as we age, and we build 2 things. We have high blood pressure. And so our vessels become more firm or tense, hardening, if you will. And then we also will start to build up fatty plaques on the inside of those blood vessels. And so the kind of most common source of stroke is one of those fatty plaque breaks off. It floats along through the blood vessel until the pipe is too small, causes a blockage. And we have the death of brain cells. You could also have a bleed. So you could have a vessel that has a weakness in it, and that vessel will break. And then you have a bleed in the brain, and that also will kill neurons. And then lastly, you can have an air or a water bubble, and that's called an embolus. Those are quite rare. You might see that after a bad injection, for example. And that would be more common in someone maybe who was self-injecting and not as careful as they ought to be. They're much more rare. Most pediatric strokes are the bleeding kind, because our vessels are very sensitive and very fragile when we're first born. And also, that's when you will typically see a vessel that's malformed actually have a breakage. In fact, your highest risk for stroke is in your first week of life.
So how does brain reorganization help someone who has brain damage?
Yeah. So what you'll see, and maybe I'll say with stroke because it's simple, but you could expand this out to different kinds of damage. So what you see is that the area around the stroke itself becomes really dynamic. That's called the penumbra. This area just outside of stroke, it tries hard to kind of take over lost function of the cells that were damaged by the stroke. So that's one way. And it operates through those plastic processes I outlined before. So you see changes in chemistry and structure and then function. Then the whole brain actually becomes very involved with time in terms of helping to recover from stroke. And you'll see distant areas taking over lost function. You'll see whole networks of activity emerge that are totally different than the networks that were there previously. And an interesting thing, because you asked about it before, is we often see that with learning, people using much more cognition as a compensation to kind of as a really thoughtful workaround the problem that they're having. And so you see these systems kind of working together to try to stimulate change. So you see the brain reorganizing kind of in a wholesale fashion. And that takes a lot of time and a lot of practice and a lot of effort. And so you'll see that continuing for it. The fastest period of recovery is in the first 30 days, and then things plateau a bit, but still continuing pretty rapidly to 3 months. And then at 6 months, you see things start to kind of level off, but you never see a stop or a cessation of change. It just continues, just at a slower pace, even well after the stroke, even years after stroke.
Yeah, no, of course. I mean, so due to neuroplasticity, does a certain skill like increase or I guess increase exponentially?
So it probably isn't exponential because that is just too fast. At least not to my knowledge. We've never mapped anything changing that quickly.
I have a new research project for you.
There you go. But what you will see is these rapid periods of change that occur in our behavior that are supported by neuroplasticity. And there's this really cool idea that we've played with a lot in my lab. It's called the challenge point hypothesis. And that is, you see optimal change when the difficulty of the task is just right. And that place, that difficulty level is different for everyone. Mine is different than yours, is different than my daughter's, who's lurking off camera, by the way. Right? But we all have one that is different. And so we now try to map these with what are called learning curves, because what we find is if a task is too easy, you're not really changing. You don't need to, because you can do it. And if it's too hard, you're not really changing because it's just too difficult. You can't accomplish the task. So what you're always trying to do is just find that sweet spot where you're getting the most amount of change in your behavior. We see that that's also the point where you get the most amount of change out of your brain. And so we've written computer programs they're looking at this rate of change. We give it a window. We say, make it like this hard all the time. And so then as you get better, it adjusts the task and makes it hard again. So we're thinking about pushing people back up that curve to keep things optimally difficult.
Right.
And I think that's kind of the sweet spot. So if you're really being challenged appropriately by your schooling, your therapist, your coach, they're keeping you in that hard zone. It's not unmanageable, but it's not easy. And so the other thing that we find is that actually failure is really good for learning. So if something's really hard and you're making mistakes, like you go to pick up your iPad and you drop it, you failed, right? You didn't squeeze hard enough, and that's a real bummer. And you remember that. And so you often won't do that twice. That's a single mistake, right? And so it's a huge amount of learning from that error. So mistakes are not bad, and learning being very hard is actually fantastically good.
Yeah, I think error is good overall. I mean, who doesn't learn from error? I mean, I always say this about people, and just in general, it doesn't have to do with the brain, but like if we were all the same, we didn't have issues, or there weren't, obviously deficits of the brain or whatnot. I mean, we live in a pretty boring world. No one would have jobs.
Absolutely.
Everything would be the same. So what's one piece of, what is one resource for people who want to delve deeper into brain health?
To learning.
But
yeah. Well, there's a few different ways to do it. If you want to be really current, there are a lot of papers published that are open access, so everyone can grab them and read them. And I always say, that's really the best way, because information is out there for everybody. Then I would remind everyone too that if you have questions, reach out to the scientist, email us. I answer as many emails a day as I can with different bits of information or websites, or would you like to be in my study? I email that back to people a lot. And so that's always a great resource. I think the TED Talks are great because they're so good at distilling and dialing things into these digestible topics. I mean, that's just wonderful, and you can sit and interact with them. And then if you like to read, there's a ton of great books. Jill Bolte Taylor's, Stroke of Genius, where she's having her stroke and she's describing it. That's a remarkable resource. And if you're interested in the history of how this came about, anything by Oliver Sacks is wonderful, because he was just at that leading edge of thinking about, why do we even have a brain? What does it mean? And those types of things. So there's lots and lots out there.
So, well, thank you so much. This was
You're
lovely.
very welcome.